Welcome everyone to our number 15 of the IAU online discourse series for the junior members. And my name is Temia Nanakara. I'm a postdoc at XMen University in Australia.
And I'm Ellie Sansom. I'm a researcher here in Perth at the Space Science and Technology Centre at Curtin University, and excited to be here.
Cool. So welcome. So I'll quickly go through what we're going to do today. So we have an exciting speaker who Ellie will introduce in a minute. So the talk will be about 30 minutes long, and then we will have some time for questions and discussions. So the best way is for you to put the questions in the Q&A tab in Zoom. Or if you're joining via YouTube, you can type your questions on the chat, and we will look at them, and we can arrange the questions to be asked during the session. If we run out of time before we get to your question, we will try to get answers for you and make it available with the YouTube link, so you can go to the online YouTube link and figure out where your answers are, for example. So we'll work something out for you if we don't have time for the questions. So yeah, Ellie, do you want to go ahead?
Yes, so with us today we have Gaitee Hussain, and she's got her undergraduate degree at UCL in London in astronomy and physics, and then became a fellow in Cambridge, Massachusetts in 2000, moving to getting an ESA fellowship at STech, and then back to St Andrews for a short postdoc before joining ESO. So most recently, she's become head of the editorial team, as well as the editor for The Messenger, as well as other publications aimed at the public scientists and senior stakeholders, and has also held a 5-year visiting chair position at Toulouse IRAP, working on magnetic fields in young pre-main sequence stars. She joined STech, or ESA, as head of science division very recently, October last year, and the science division hosts the project scientists working on all of ESA's science missions, and 25 research fellows, several trainees and interns, and she supports the faculty and science communication and education initiatives. And today she's going to be talking to us about adventures with ESA Science Missions. And basically, this is a program is incredibly diverse: missions that circle the sun, relay messages from Mars, find new solar systems, map our galaxy in exquisite detail, and even probe the origins of the universe. So in this discourse, she's going to take us on a journey through some of the most exciting recent findings to come out of the science missions, and what the future looks like, and what we can do together to make sure that the full potential of these missions is realized. So take it away, Gaitee.
Thank you so much. So it's quite a broad remit that I'm going to try and fulfill within 30 minutes. So I shall do my best. Let me first check that this is this good to go?
Yeah.
If that's correct. Okay, let me see if I can move this up. Okay, great. So, so as I said, in the next 30 minutes, I'm going to take you on a selective journey through some of the science that has come out from the European Space Agency's science missions, and what we're doing within the agency, working with other parts of the agency as well, but also with our partner space agencies across the world. So thanks for the lovely introduction, Ellie. So I recently joined again the European Space Agency, as I'll discuss later in the talk. I'm actually coming back after 15 years away, and I was a postdoc here very early on in my career. So it's great to be back and get a completely different perspective on working in the European Space Agency. Just a brief introduction, very brief introduction to the European Space Agency. We exist thanks to the work of 22 member states and the contributions of 22 member states, whose flags are shown along the bottom, along with some associated countries. And we have 7 sites across Europe that host 5,000 employees. And the main sites that are concerned with the science program and the science missions are outlined in blue. So ESTEC, the Netherlands, where I'm based currently, is host to where the missions are defined, they're in study phase and developed, mainly at ESTEC, working with scientists and engineers here. And the project scientists in my division also mostly reside or rather work at ESTEC. ESOC is our center in Germany where the missions are flown from, and so they handle the tracking of our space missions, the satellites, and do essentially execute the planning that we need in order to get the science observations that we need, and also everything else that we need to get the spacecraft where we need them to be to carry out the missions. ESAC in Spain, just outside Madrid, is where the science operations are centered, and also where our archive efforts are very much a focus. And additionally, of course, French Guiana and Kourou specifically is important, as it is where many of our missions are launched from. So the European Space Agency has 4 main pillars, which are described here in these bars at the top of each of these squares. So science and exploration is a core pillar of ESA. In fact, the science program is a mandatory program, so all the member states contribute to it. And we work very closely with our colleagues in human and robotic exploration, which is where the science exploration tag comes from, in maximizing the scientific return from missions that both directorates run. But even though science resides within this pillar, we of course rely and work very closely with all other parts of the agency in order to have and run successful missions. Now, a question that's commonly asked is, why go to space to do your science? It's significantly more expensive than doing it from the ground. What are good reasons to go to space? For the 3 different scientific areas, main scientific areas that we cater for with the science missions, helioscience, planetary science, and astronomy, there are a number of reasons where it's advantageous to go above the Earth's atmosphere or get closer to the objects themselves, in the case of solar system missions. So for helioscience missions, you can get closer to the sun, you can take in situ measurements at various distances, probing different parts of the solar atmosphere and the solar wind. You can fly over the solar pole, which is a vantage point we cannot get from Earth. And so you can see missing parts of the puzzle of explaining why the sun works the way that it does, fundamentally, in the case of the solar dynamo. For planetary sciences, we get, by flying and orbiting the specific planets and sending probes in, we get to study dynamical processes, chemical processes, and geological processes in detail. By combining the data that we get from orbiters and landers, mainly working closely with other partner agencies, we can sample the composition of the planetary atmospheres at different heights above the surface, and again begin to understand the origins of the composition and the processes that are leading to regenerating those atmospheres continuously, or in fact, in some cases, losing those atmospheres. In astrophysics, naturally, as with the other missions as well, if you get above the Earth's atmosphere, you can access wavelengths that are simply blocked by telluric absorption, for instance. We also escape the blurring and variability of the Earth's atmosphere, so you can get more stable, more exquisite images, or more precise, more sensitive measurements over longer periods of time, get stable time series of data for missions, for instance, looking for exoplanets, planets around other stars, or looking for instance, getting astroseismic measurements and actually trying to probe the sound waves to probe the interiors of stars as well. We have an enormous number of missions. We have several missions that sort of fall broadly into each of these scientific areas. Here is a list. I don't propose to go into these in particular detail, but there's always several missions that are in operations that we're running. There's, at the same time, there's usually other missions that are in preparation, and a certain amount of missions that are in legacy, but we're still working to maximize the scientific return from those missions also. And And in total, we have 13 missions in operations currently, and there's 16 missions now that are in preparation within the next decade. And we're already exploring themes for going further than the next decade. The timeframes for space missions are long. This is a snapshot of our family of solar system explorers. These are the ones that are in development. These are the ones for the future. These are the ones that are currently in operation, and these are the ones that are in legacy. And you can broadly divide them into solar missions, ESA Science Missions, and planetary science missions that are outlined in the blue boxes. These are the ones that are currently in operation, but we have some very exciting ones coming up. And there's a lot of effort that goes into ensuring those missions can deliver on their full scientific promise. On the astrophysics side, these are our cosmic observers, as we call them. These are the ones that are currently in operations. These are the ones in development. Webb is up next. It launches in November. And it's not exactly a counterpart to Hubble, but much like the other observatory type missions, it's designed to address a variety of scientific themes. Excuse me, I'm going to sneeze. It's designed to address a variety of scientific themes, and it's probing the universe in near-infrared, mid-infrared wavelengths. And so it's going to be looking at first galaxies and stars, galactic evolution in early time, and looking at the life cycles of stars, how stars and planets form together, and ultimately also what their fates will be at the other end of the equation. When stars die in supernovas and release a huge amount of chemical material into their environments. And obviously currently we have Hubble, XMen Mutant, and Integral, and we work very closely with communities to make sure that they're getting the most out of these missions. But let me get on to the science. And I just realized that I'm not actually tracking my time. Here we are. So for the solar system missions, we have a number of them. Let's start closest to the sun. This is one of our grand dam sort of solar missions. It's SOHO. It has been running for 25 years now. It celebrated its 25th anniversary last year. And what you see here are snapshots of images taken every year that it's been in operations at extreme ultraviolet wavelengths, so really probing the 2 million degree corona of the sun. And you can see two full activity cycles have been measured and mapped in exquisite detail, not just in extreme ultraviolet wavelengths, but actually in multi-wavelength, using multi-wavelength instrumentation. And so again, really probing multiple layers of the solar atmosphere. This has given us great insights into how solar storms are created. It's given us a greater ability to predict coronal mass ejections, which are these giant solar storms, and get 3 days warning for things that are headed our way. Because of where the SOHO satellite is situated, you can actually measure in situ particles when they come our way as part of coronal mass ejections. SOHO serendipitously has become an enormously successful comet hunter. Amateur scientists have detected 3,000 comets to date using SOHO data, as comets, of course, are many of them are sun grazing, and so that data just comes in serendipitously, and the data is available in real time. And we have an enormously enthusiastic community out there that's helping us characterize new comets. Solar Orbiter is our latest solar explorer, and it was launched early last year. And here you can see how its flight trajectory will change from its initial launch. We are using the inner planets as gravity assists, essentially. So we have a number of flybys with Venus and Earth, which allow us not only to adjust the trajectory of the spacecraft itself, it also allows us to adjust its inclination. And so in subsequent flybys, its inclination is actually going to increase to higher and higher inclinations, up to 24 degrees within the nominal mission. If it gets extended, it will even go up to 33 degrees out of current plane. And that means that we get better views of the pole than have been possible before. And in the next years, the sun will be entering solar activity maximum. And so we'll really get to see how the poles, what part the poles play in determining various aspects of the solar magnetic activity cycle, which is something we cannot get from the ground itself. So Solar Orbiter is host to a suite of both remote sensing information, instrumentation, but also in situ instrumentation. So it's going to be detecting particles, studying particles, energetic particles. It has a magnetometer. It's going to be getting magnetic field maps, as well as imaging the heliosphere and the corona of the sun as it changes over the next years. And that one of the core questions, scientific questions that Solar Orbiter will be addressing is how the sun creates and controls the heliosphere. And the heliosphere is, of course, this vast bubble of sort of charged particles that the solar wind ejects out. And at the outermost part of the solar system, it essentially starts to interact with the interstellar medium, creating this sort of bubble in which our solar system is situated. So I won't go into this in a huge amount of detail, but we have a mission called BuffiColombo, which is heading towards Mercury. It's Europe's first mission to Mercury. And this is working in collaboration with JAXA, which is the Japanese agency. There is going to be a Venus flyby coming up in the next 19 days. And these are opportunities. So BuffiColombo has been launched. It's essentially in its cruise phase. But various flybys that we have help not only obviously to control its trajectory, but also to enable us to calibrate the instruments and do science, essentially. Also working together with our other satellites to get complementary observations and as I said, calibrate the instruments. When it gets to Mercury, it will begin to probe the origins of Mercury's magnetism. There are not so many magnetic bodies in the solar system. The Earth is one of them. It's an extremely important component of the Earth for our survival. So understanding magnetism in solar system bodies is actually an extremely important thing to do. But it will also be studying the structure, composition, and dynamics of Mercury's exosphere. And this gives us insights into what a planet that close into its host star is subject to, and how that might affect its evolution, which is really important for us to place the various planets we're finding around other stars, many of which are very close to the host star. It allows us to place those in context as well. Venus, again, I sadly won't be spending a lot of time on this, although there is a lot to say. Envision is the latest announced mission that we're going to be working on at the European Space Agency. Its launch is planned for 2031, and it will be going to Venus and getting a comprehensive overview of Venus from its interior to its outer atmosphere. So it has a very powerful suite of instrumentation to enable it to do that. I'm skipping over the Earth, but actually we also work very closely with our colleagues in Earth observation, and we also have spacecraft orbiting the Earth, which enable us to do plasma physics experiments, which are also, of course, extremely important in understanding the Sun-Earth connection and the solar heliosphere and solar wind as well. Let me spend a little bit more time on Mars. Simply for the reason that we have so many things happening around Mars and coming up on Mars in the next years. So Mars Express is our long-lived orbiter that has been orbiting Mars since 2003, so almost 20 years. And in that time, it has given us impressive insights into the atmosphere of Mars, how it changes. It's allowed us to map the surface of Mars in exquisite detail, and I'll talk about more about that in a second. Our second orbiter is a trace gas orbiter, which is geared towards, particularly towards detecting signs of biomarkers in the Martian atmosphere. Next year will be an exciting year. We are working with our colleagues in human and robotic exploration to support the operations of the European lander, which will hopefully happen at the end of next year, and that will be our first, hopefully, landing on Mars, and on which we can operate the lander. And starting from 2026, there's a Mars sample return exercise, which is a series of missions which we're working on with our partners in NASA, which aim to bring back pristine samples from Mars to Earth so we can study them on terrestrial labs, where we can extract a lot more information than is possible on site within the instrumentation we can fit in rovers themselves. I wanted to show you some of the just absolutely beautiful imagery that has come from, thanks to Mars Express. Here you can see an image of the Korolev crater, which is 82 kilometers across and 2 kilometers deep. Its depth allows it to have this permanent presence of ice in the center, as the air above it essentially cools and acts as a kind of insulation layer, and so it prevents the ice underneath from sublimating when it's exposed to radiation. And you can just appreciate the absolute beauty of this kind of imagery, but also it gives us insights into how water ice is distributed on the Martian surface, and try to understand the history of water on Mars, which of course is a burning topic for many reasons. Here is another example of just some beautiful images taken. This is the glacial region on Mars called, I wrote it because I can't ever remember it, Deuteronomus Mensae. And again, here, the ground resolution is about 21 meters per pixel. And it again allows us to probe the history of the geology of Mars in exquisite detail. The other thing Mars Express is helping us do is characterize the regions around which rovers are going to be operating, or are operating. In fact, this is the region around the Jezero crater where the Mars Perseverance rover currently is. So this is the region around it, and here you have the Terrae Sabiae, which are highlands in the region, and this is the Jezero crater. And so we get to understand the history of the region in which it's forming, and also to characterize the landing sites for our rovers themselves in exquisite detail. Now, the other thing that Mars Express has enabled is to understand its water history, and having almost 2 decades worth of observations have allowed scientists to characterize the amount of water loss from Mars in different seasons. Generally, the findings are that water vapors can find to lower altitudes at aphelion when it's more distant from the sun compared to at perihelion. And this allows scientists to model the amount of atmospheric water loss you expect just purely due to not only seasonal changes, but also dust storms. However, what modeling indicates is even with the atmospheric water loss at current levels, it's not sufficient to explain the evidence of water that we see on the surface, the relics, the glacial features, the ice that we're finding. And so there are different explanations for where the water might have gone on Mars. And this is still a burning question, and it's something that our missions are actively contributing to. So Mars TGO is our latest orbiter, trace gas orbiter, and it is working closely with Mars Express and with landers to understand changing variable detections from methane that have happened on Mars over the years. So dating back to 1999, there were ground-based observations indicating that there were higher levels of methane than one might expect. Now, methane is a particularly interesting gas because it might have a volcanic origin or geothermal origin, or it might have a biological origin. Mars Express, at various points in its history, has detected variations of methane. And lander certainly has detected methane spikes every so often, but when we've had more coordinated observations or closer in time observations between the orbiters above the Martian atmosphere and or in the Martian atmosphere and the lander, there are discrepancies. And so understanding how methane is being produced and what its fate is something that is still very much an active topic of conversation and study in the Martian community. ExoMars Trace Gas Orbiter is also designed to get measurements for other key biomarkers, including ethane, ethylene, and phosphine. And at the moment, it's placed very sensitive upper limits. But of course, there's a lot more data to come. And again, we're working closely with the landers and with other agencies that are arriving at Mars is very important. Rosetta is a seminal mission for the agency, and I'm sure everyone has at least heard of it. This was our spacecraft that went to the comet 67P Churyumov-Gerasimenko, and it had the lander called Philae, which had a soft landing on the comet. I'm going to spend a criminally short time talking about Rosetta, sadly, but the point that I wanted to make is that there's still a lot to be, we learned a lot about the composition of the comet, about the geology of the comet, which is, of course, one of the pristine remnants of the leftover from the formation of the solar system. But semi-pristine remnant from leftover from the formation of the solar system. But there's still a lot that's coming out of the data. In fact, just last year, there was a paper that was published analyzing observations taken of the touchdown site. So Philae, the lander, sort of had a soft touchdown in a particular region, then it rebounded. Based on the data that we have from its journey across the comet, there was actually a study that could measure the porosity of a particular region on the comet, and found that it was very much in line with measurements that Rosetta was taking of the entire comet. And what they found essentially is that the softness of the material where Philae landed is essentially similar to sort of the froth of a cappuccino, or if you prefer, the head of a pint of Guinness. Now, let me very quickly get through our some science from our astrophysics missions. So here are the ones that are currently in operations, as I said. Because I've been talking about the solar system, I wanted to spend just a minute on talking about the various spacecraft that we have and the various missions that we have that are allowing us to do different kinds of science on planets around other stars. And so Ariel, Plato, and Cheops are specifically dedicated to detecting planets around other stars, and in the case of Ariel, actually measuring the composition of the atmospheres of roughly, in its case, about 1,000 planetary atmospheres. And this enables us, in combination with the body of science that's coming out from the planetary missions, to really try to understand the origins of exoplanet atmospheres and understand how they might evolve, or at least place them in context. Plato is a mission that will be coming from 2026. And it's a huge survey. It's going to be targeting about 1 million stars and looking for, through the transit method, trying to calculate the radii of numerous sort of Earth-like planets. And the plan really is to get down to Earth mass, Earth-sized planets with that mission. With Roman, there will be microlensing planets, are a key component of the mission, which we are doing in partner with NASA. So we're more junior contributors in that mission. Webb will have exquisite exoplanet and star formation. Exoplanet and star formation atmosphere detection capabilities, and it will also be investigating brown dwarf atmospheres, which are essentially the failed star slash sort of they fall between the star to planet regime. So there'll be a lot of planetary science that will be coming out of Webb itself, or even though it's not its core science. Hubble has already contributed a lot to our understanding of exoplanet atmospheres, particularly for hot Jupiters, which are very close in Jupiter-sized planets, close into their host stars. And Gaia is also providing will be providing much more information on planet detections and allowing us to confirm planet detections more precisely just through the high precision astrometry that it will be getting. I will be spending very little time on Hubble. I almost think Hubble needs no introduction. It celebrated its 30th anniversary, and this was the image released in celebration of that. But essentially, it's contributed to almost every area of astrophysics, from cosmological science to star formation to planets and everything in between, of course. And it's captured the imagination of the world in many ways. XMen Mutant is our X-ray observatory that's been running for over 20 years, enormously successfully. It has a wide field of view, and it's been essentially mapping mapping and monitoring the hot universe. It possesses a very sensitive spectrometer, which allows us to measure X-ray fluxes and densities and abundances in huge amounts of detail. It has made advances in the fields of neutron stars, in understanding the regions around black holes and the energetics around black holes, tidal disruptions, transient events. It's contributed a lot to our understanding of star formation and the energetics of young stars. And one of the key results that's indicated by this infographic kind of slide shown here is it's allowed us to measure the amount of hot gas, essentially, that is a key component of the normal matter in the universe. That's only 5% of the universe, but it allows us to find some of the missing normal material that essentially hides the intergalactic material medium, which is detected as absorption in between X-ray observations. In X-ray observations of distant galaxies. And Gaia is an absolutely revolutionary mission that is measuring precisely the positions and promotions of 1.7 billion stars in the Milky Way. Every picture that you see here is a star that has been measured. In just a few years, Gaia has become essential to galactic science. It has now been used in over 4,000 publications, Gaia data, and in itself, it's contributed an enormous amount in understanding the galactic history of our own galaxy. And here you can see this movie based on simulations to understand Gaia data of the interaction between the Milky Way and the Sagittarius dwarf galaxy. And from these simulations, which reconcile the history of the Milky Way with Gaia data, you can see that there are multiple sort of interactions between the dwarf galaxy and the Milky Way. And in fact, one of these interactions appears to happen at about the time of the formation of our solar system. And that is particularly interesting, potentially interesting for understanding the history of our own solar system. A recent result, which I won't spend a lot of time on because I see my time is ticking, is understanding the mapping the spiral arms in the Milky Way and tracing their origins using open clusters. And by doing this, so these are different arms that were traced by mapping different open clusters. and various statistical techniques, and trying to understand the origins of spiral arms in our galaxy. This is just to illustrate some of the science Gaia is enabling. It's actually doing much, much more. It's transforming stellar astrophysics as well as our understanding of our galactic history. But I will skip on. I hope that in my very quick journey, I have demonstrated that to you that the ESA Science program is incredibly diverse. I haven't even touched on everything, all of the kinds of science that we're covering. I haven't even managed to touch on every single mission, but there's a lot going on. One thing I wanted to say just before concluding is that we work really closely with the scientific community and ESA member states. And so we work very closely with you. You help to define the science themes, you help with the selection of individual missions. And when the mission has been selected, we work very closely with you in making sure we can maximize the science. The next big science themes have been announced. I'll leave that slide up at the end, and we'll skip over this very quickly. I think I'm pretty much done. We have various research programs which are good for early career scientists. And in particular, there's a research fellowship program, which is open to nationalities from our member states. And I think I'll stop there and just take your questions, but I will just for 1 second show you what the Voyage 2050 themes are. And these are for missions that will extend from 2035 to 2050 and beyond. And this, of course, is very much the science that I guess many of you will be doing. Certainly I will be retired by then, but it's absolutely thrilling to be able to see and to try to enable the science that will be coming in the future. So thank you very much for your time, and I'm really looking forward to your questions, and I will stop sharing now. Thanks.
Thank you ever so much, Gaitee. It was a fantastic presentation. I love seeing some of the pictures from ExoMars again, and I guess Demian, do you want to take it away with questions? So just quickly again, if you have any questions, pop them in the chat box, either at the bottom of the YouTube, on the YouTube channel, or in the Zoom chat box, and we'll go through those as well.
Cool. Yeah. Thank you very much for the talk. So I'll ask something that you didn't touch much, like because the news there was about the ESA, the astronaut selection that was going on after many years. Like, do you have any information about that? Like, have people been chosen and like things?
So I believe the selections are happening. We had a press conference. So I should give the first disclaimer that this is not the science directorate. Does not work, sadly, with the astronauts. I know several of the scientists in my division have applied, so we'll see what comes out of that. But yeah, as I understand it, there were over 22,000 applications. There were about roughly a quarter from women, which we were really happy about because it was much fewer in the past, but obviously we'd want to do better in the future. But yeah, so and we had 257 applications for the para-astronaut call as well, which is for people who are differently abled. And so we are, so we're really great. We're really thrilled that so many women have applied. There is a long selection procedure. It is not straightforward, as you might imagine. So initially, there is a screening questionnaire that is happening, that's being assessed. There are psychological assessments that go through. So in that stage, 1,500 will go through of the 22,000 or so that applied. Then there's going to be practical and psychometric evaluations, medical evaluations, and interviews. At the end of that, at the end of all of that, there'll be 40 people standing, roughly, more or less. And then from that, there'll be 25 chosen. So essentially, there are 5 astronaut positions, 4 to 6 or something, career astronaut positions, where that will be their job, and that will be what they do full time. But there will be 20 people that the agency is hoping to hold in reserve. So you would continue doing your day job, but almost like a spy, you could be called on by the agency when required, when needed. There are a number of activities coming up that will require astronauts. So ESA is getting involved with the Lunar Gateway project, which will be this orbital station further out from the International Space Station. There's plans to come in on the project to settle essentially on the moon, and also, of course, to eventually go to Mars. So there's a lot of work happening, and there will be a need for astronauts, and the space sector is growing. And so there will be more coming. But so we're hoping the pool of 20 astronauts will be people that we can call on when we do.
That's pretty cool. I guess to get your science with ESA, it's trying to get onto one of these missions as well. It's just as exciting. So,
I mean, the other thing that our talent recruitment agency has been emphasizing, and it's true, is that at the European Space Agency, we're getting what we're calling a retirement wave, essentially. So a lot of people hired about 20, 30 years ago. And so even if, you don't get an astronaut position, there will actually be many opportunities coming up in the European Space Agency in the next years for engineers, scientists, communications people, all kinds of areas. And so again, they're open to people from ESA member states, but I think it's a really great opportunity to be reinvigorating how the agency.
That's actually one of my questions was your background. You've kind of been through quite a few of the different branches of ESA, and I was just wondering what you kind of maybe enjoyed most about kind of SOC versus STech, or the different branches.
So I haven't worked at the different branches. I've been basically at STech the whole time. But yeah, so I think there are very different disciplines. And I mean, certainly we work very closely with engineers. And I have to say, I think there's a very healthy and different perspective that scientists and engineers have, right? So scientists are always interested in, well, I mean, of course, we should try to push the instrument, even at the risk of the instrument. Yeah, I'm not saying that that's what our scientists do, but, the science is what's driving us. It's just like, oh my God, wouldn't it be so cool if we can make this observation that's never been done before? But the engineers are really interested in the art of the possible right now. And so they're constantly kind of pulling us back and saying, okay, this costs this much money, right? So you have to come back into the thinking. And I think together we create brilliant things. But there is necessarily always a healthy tension between what's happening on both sides. Similarly, we are working very closely with the archivists and the archive data scientists at ESA currently. And on that side, we have to continuously think about how to make even older data that we have from our missions that are now in legacy phase accessible and usable in new ways with the new technology and our best understanding of what open science looks like going to the future. And so that is a continuous effort, and it requires continuous learning on that side, which is different from maybe not answering specific scientific questions, but thinking about how to make things accessible. And that's a whole field in itself. So yeah, there's many different jobs.
I was just thinking about that as well, with trying to having missions that have been going out for so long, and like the solar orbiter, or the original one that's been working for so long, and you're getting that continuous stream of data that, digging into that archive data must be really, really interesting at trying to actually now start. You're not just looking at current observations, you're actually looking at the change and how things are actually progressing, which is pretty cool.
Absolutely.
So something related, in your talk, you mentioned that Rosetta, when it started with the 1970s, right? The idea came about and then like took up to the early 2000s to get the mission going. So when you say this discussion between engineers and scientists and like the financial part of things as well, like what kind of a timeline is normally like is what ESA looking at in the future for such projects? And what's the main drawback? Is that the technology is not there, or is it like more like a combination of things that play a role in the lengthy timeline?
So there are different things, right? I mean, it depends on the ambition of your mission. So, I mean, we do also we do different things. So we're constantly testing technologies. So for instance, we're working with the national space agencies that are in our member states to continuously be testing tech. I mean, we have a number of CubeSat experiments that we support, run, help place contracts with industry, use our know-how with, to test really sort of risky future technology in order to test it now so that it might be used in the future. So even if we don't have a mission in mind for it, it's activities that are continuously going. We have some missions that have been from concept to launch have been much faster. I mean, I think Rosetta is a particularly strong, a particularly significant case. It's not that all the missions work like that, but yes, there are constraints, right? There's constraints on the budget. We cater to different communities, and so we have to always work with those communities to help them decide, then they decide what their priorities are. So if they wanted to do something faster, it can probably be done, but it requires an extra investment. And we're very much guided by the scientific community in those decisions. We don't make those decisions. But often, as the plan is for Voyage 2050, which are missions that are going to be between 2035 to 2050 and possibly even beyond. So that we're looking and really pushing the technology as far as it can go. And that requires us to start working on the technology now and brainstorming in the technology and bringing in industry, bringing in scientists and working out what is possible and trying to work out what will be possible in 14, 15 years. So it's a tough exercise, but if you really want to do something novel, then that's kind of what you need to do. Also, I mean, the other thing is that it's obviously space is, needless to say, a very different environment from the Earth. So we may have technology that we can try all the time out in ground-based instrumentation. I worked on ground-based projects for the last 15 years, and those you can do all kinds of risky things because you just know that you try it, it doesn't work, you can walk away. If you launch something that might potentially destroy your spacecraft, that's a very different conversation. And so we have to be very careful and very responsible about what we do. And so making sure all of those boxes are ticked necessarily takes time. It's just a process. But as I said, there are some missions that we do much faster. The follow-up to Rosetta is Comet Interceptor, and that's being planned now, and that will be launched alongside Ariel. It'll be piggybacking in the same launch as Ariel, and that will just be in 2026, and it's just in study phase right now. So that's a relatively fast mission. So it kind of depends on the scale and the ambition of the project that we're trying to achieve. And we try to have a diverse range. So we try to have the less risky things that are possible now. KOPS might be an example of that, where it's a small project, it's going to do one kind of science mainly, and it's much cheaper as a result, as compared to JUICE, which is one of our large missions that will launch next year, and it will go to the icy moons of Jupiter. And that takes
yeah. Oh yeah, I think that gets a better idea of like how the missions work. I guess like one thing is also like you have projects that are looking down on Earth as well, right? For example, like with climate change and stuff.
Yes.
Like does the ESA Education in ESA department, do you work on like looking into polar ice caps, carbon dioxide, and I don't know what? Yeah.
So there's a whole suite of Earth observation satellites, and that is what they do. They are looking at exactly that: ice, tracking storms, producing imagery to support flooding, which is unfortunately a very big thing at the moment, tracking fires, continuously monitoring. We also have the Galileo program, which is one of the best satellite navigation systems that's run through the European Space Agency. Again, that's outside the Science Directorate, but it's something that we're also interested in. As I mentioned earlier, some of the Earth observation satellites are also touching on plasma physics experiments, and that kind of then brings it more into the science regime. But there is a lot of work happening with the Earth observation side, and we're working increasingly closer with the European Union as well on the climate change directives. And as part of that, the European Space Agency also has its own green program aiming to cut its emissions compared to 20, 30 years ago. So we have specific targets that we're aiming for as well.
So we've got a question that I guess quite relates to this as well. They ask, can you please say more about how the ESA scientific vision for 2035 to 2050 came to be? And with so many mission ideas being proposed, how does the committee decide, and how can science and technology be balanced? There's quite a few little bits in there, but let you answer the bits you want.
Sure. Okay, so generally it's kind of a 2-year process, more or less. So it kicked off about 2019, we worked with our advisory bodies. Everything we do is with our senior science advisory body, which is called the SPC. They agreed with us on a senior committee that selected from scientists covering our range of science that we cover from the community. They worked with us to form, I think it was 4, maybe 5 topical working group teams. So they were focused on specific areas like stars and planets, or cosmology, or planetary science. And those brought in a mixture of scientists from different stages of their career. And one of the big focuses in this round, and I don't know exactly how much had happened in previous rounds, but certainly in this round, we had a big focus on recruiting early career scientists, because we are building these missions for those people, right? For you, essentially. And so they looked at over 100 white papers were submitted by the community, and they had to work their way through it. It's not a simple exercise. They had to work through it, and they had to, again, even with their evaluation, they had to evaluate what would be really important to do, and what we might be ready to do. And so one of the big recommendations that has come out from Voyage 2050 recommendations, and I invite you to read the full report from the committee itself, which is very interesting, is to develop technology as well, because one of the things is we don't run nuclear powered space missions as an agency, and that limits how far we can go into the outer solar system. We just can't get sufficient power. And so working on technology to allow us to develop sufficient power that we can explore the outer edges of the solar system, even beyond, is something that's obviously extremely attractive. But we have currently technological limitations, and limitations on how the limits the agency sets for itself as well. And so there's aspects like that, and that's just one example. But there's also quantum technology that's coming. They recommend that there's various technological areas that also need to be a focus. So again, not necessarily tied in with the mission for the 2035-2050 timeframe, but things that we need to start thinking about right now and investing money in, that the member states need to be investing money in right now. But for the missions themselves, it was picturing which missions we have coming up. So for instance, JUICE, and trying to work out what science they'll be returning and what we'll need to be building on next. So for instance, in exoplanets, and I mentioned that because that's sort of closer to my research area as well, is we know that Ariel will be characterizing the atmospheres of hot planets, basically hot to warm planets, so things that are quite close into their parent stars. But what we really want to be getting to at that point, because Plato will have identified all of these beautiful, hopefully, Earth to Neptune-sized planets, then we'll want to be characterizing those in the kinds of distances that we're interested in for, habitability, as however you want to define these things. But certainly more temperate planets, as they call them, and that would be an extremely attractive thing to do. But we need to really think about how we do that, because Ariel already is really pushing the bounds. In fact, we're working on making the technology push the bounds of what is currently possible in order to achieve Ariel's goals. So it requires us to be extremely ambitious, but to set the train running now, so that we are ready when we're ready to launch and really do the most we can.
That's great. So given the time, maybe the one last question that has come through is about a citizen science project. And slightly rephrasing it, it's how do you encourage people to participate in astronomical citizen science projects? And if you have any projects that are suitable for blind or hearing impaired personnel, so where they can use that as a hobby or like to do something in the free time, kind of an idea.
That's a really good question. So we have citizen science projects that we're running. We have one on Hubble currently, but and it's been in a very effective detector of asteroids. Again, we're just finding asteroids wherever we look. But also there's two more that are in the works. One will be for Rosetta, in fact. So it'll be citizen science just building on the huge archive we now have of data that was collected for Rosetta. And identifying features on the comet and enabling us to characterize them better. But in terms of visual impairment, it's a good question, and I don't have a good answer to that, but I think it's something that we should be doing. So that is something that I will be working on, because I think that is an excellent point. Currently, it's true that they're very much visually oriented, and so they require you to be identifying particular features. But I think that's a conversation I need to be having with people in ESAC, and I will be having that. So thank you for that feedback, and we will be working on it, because I think it would be a really valuable way to work together with the community.
Great, yeah, thank you for the person who asked the question. It's good to bring up these things, right? Yeah, I think given the time, we should wrap up here, I think. So thank you very much for the talk. I really enjoyed it and learned a lot of things about different missions, and the discussion was also very informative. So I really enjoyed it. Thank you for your time. And for everyone, thanks for attending as well. So this is our one before last event. So our next month event would be the last one for this series, and for the working group, organizing committee for us, basically, because as you may know, in August, we are having the new committee coming in. And if you haven't voted yet, don't forget to vote. You should have got an email. And our next event will be on August 19th. It'll be at 2 p.m. UTC or 4 p.m. CEST. And it'll be Professor David Spurgill from the Flatiron Institute, and he will be talking about open data, open codes, and astronomy. So that'll be our final event, and we hope to see you there. And thank you very much for joining.
Thank you very much.
Bye.